introducing what quantum computing is and what quantum machine learning is. Before that, I want to discuss the machine learning project workflow we usually use in industry to solve machine learning problems. And uh, I'll also elaborate on why quantum is important and where we stand right now and what are the research scope as a faculty, what we can do and what is the research scope in quantum machine learning and all. I'll also touch upon supervised quantum machine learning algorithms I developed in my during my PhD. So yeah, so this is the concern for everyone. Data everywhere. So you can see the amount of data that is being generated every day, every second, and huge amounts of data is being generated, and we need to process that information, data, and get some information and insights out of it, so that we can use those insights for building products or taking decisions or improving our lives and all. So with the huge data growth, so if we properly use the data and if we can perfectly get some insights out of it, we'll be able to get the answers that we are looking for in the data itself. So if you see the exponential growth, so just in 2018, around 33 zettabytes of data, and it is expected to reach 175 zettabytes in 2025. Actually, this is published in November 2018, but I guess this number would definitely increase by now. So with that, as the amount of data is being generated, people started looking at big data and the properties of big data, the volume, velocity, variety, veracity, and value. So the volume at which the data is being generated, and the huge amounts of data, and velocity at which it is growing, and different types of data being generated. So right now the research is at the stage of multimodal transformers, where we give multiple text and image prompts as input, and you will be able to simply generate whatever you want out of those machine learning models. So even variety of data is being collected, and the models are being trained using that. Also veracity, the quality and trustworthiness of data is very important, because in machine learning there's a principle that if we feed error into the model, it gives you the error as output. And the value. So after analyzing all these, say if I spend some thousands of dollars to analyze this and get only some $50 value out of it, it is not of anybody's interest. So value is also very important. So there are many applications. So specifically into geospatial data analytics for big data, and social network data analytics, fitness analytics, stock market prediction, search analytics. These are a few, but there are a lot. So after introduction of machine learning, big data gained more prominence, and machine learning actually helped big data growth a lot. So the research on big data growth a lot. So traditional programming, we use data. Yeah. So traditional programming, we use data and we use program together, and we feed some system and we'll get some output. But in machine learning, so we have some data and we know the output for the data. And now we ask the machine to learn the patterns from this, so that it can predict the output whenever we give some unseen data as input. So this is specifically to supervised machine learning, where you have data along with the output together is fed into the machine learning model, and the model learns from the data and you get the output, predicted output on the unseen data. So this is pretty obvious thing. And yeah, so now these are the three main components: data, model family, and loss function. So you need good data. So right now, Android is working on the data-centric AI movement, where the model-centric AI is no more preferred, where only data-centric AI is preferred, where data is crucial in building any model rather than just the model's architecture. So coming to the models architecture or the model family, you'll have you'll be computing the function using the machine learning strategy. where you have some input data and you have trainable parameters. Based on that, your machine will compute a function which will learn the patterns from data. And the loss function, so it is to penalize the learning, and it will try to find out what is correct and what is wrong, and based on that, your model will be trained, and this simple back propagation, all these things. So now let us look at any machine learning or data science project workflow. So the first and for these are the steps usually almost all the problems in industry or even in problems that we solve in the real time will be used. Uh, uh, these steps will be used in for that particular sense. And coming to the first step, so you need to understand the requirements very carefully. So because requirement understanding, you should define the problem very carefully so that it actually reflects the main solution for of that. So now coming to the data acquisition. So once you understand the requirements, you need to acquire the data very carefully so that uh, this data is perfectly suitable to solve that particular problem. So for that, you can rely on extract, transform, load. You can also have SQL kind of things. You can have you can pull the data from databases or data warehouses. Even log files will contain some kind of information in order to solve some problems. And of course, if a problem is on a very large scale data, so you can always take help of a Hadoop cluster or Spark cluster to pull the data and work on that. And most important step is data preparation, where you clean and pre-process the data. Believe me, almost 70% of the time, or 60 to 70% of the time, data scientists or machine learning engineers spend is on cleaning the data and pre-processing. Because once this is done, it is very easy for us to train the model on this particular data. And coming to exploratory data analysis, this is very crucial because simply by plotting, we can solve some problems. We don't need to learn from data. Just by visually looking at the data, I can say that, okay, my sales are increasing in March, or my air conditioner sales are increasing in April, May, or June, something like that. So just by looking at that, I can simply visualize and I can solve the problem. I don't need to go for machine learning, waste my resources, waste my company's time or something. And then, so now, as you have enough data and you have plotted the data and you understood what data is, how can you use the data and how can you handle the data, you will be perfectly designing the model and you will be evaluating the model with many performance metrics like precision, recall, plotting, confusion matrix, and all these things. And then you interpret the model. So I'll come back to this interpretation because not all the models are interpretable. So some models in machine learning are interpretable, like decision trees and all. And so it depends on the problem. So if your problem or if your client asks you to design something which is interpretable, you should carefully select such kind of modeling on the data. And next, we'll observe and we'll record the results. And then we deploy the models in the real time to test the models. And then, so once we test the models and we deploy it, you'll be able to understand in what cases it fails. And then you again retrain the model and you change your process of training or something. And then you again improve the models, collect more data. If this particular data is not sufficient, again, you try to collect more data and you collect more features and you optimize your code. So this is the usual data science or machine learning workflow that almost all people use in order to solve problems using machine learning. So I'll tell you why I've highlighted this data preparation, modeling and evaluation, and interpretation and optimization. There is some relation of for these three steps with quantum machine learning. I'll come at the end. I'll explain that in the end. Right. So yeah. So now, if the data complexity increases, definitely you need to take it as a concern. So as the amount of data that you are handling is increasing, definitely you need to look at what are the challenges that are being posed by that particular scale. So usually, so dimensionality uh, of the data will be increased. The number of class labels with respect to supervised machine learning also increases. And there is a chance that you might collect some imbalanced data. Say, for example, when we consider bank defaulters, so out of 100, there will be some 20 cases of defaults, if not even 20. So that way you have very imbalanced data for non-default cases and default cases. So for non-default cases, you have 80, and for default cases, you have 20. And you will also get some noisy data and also inaccurate data. So then it challenges the efficiency of the machine learning algorithms, interpretability, accuracy, and also if you are executing or training your model for much time, energy is also a concern. So increase in training parameters, the model selection becomes difficult. There will be huge drastic change in the trainable parameters. If you see the transformer kind of models are taking some billions of parameters. Of course, they are performing absolutely perfectly. And computationally efficient hardware is required, and we also require memory intensive algorithms, right? So now, so coming to the challenges that these things are posing. So we need to scale our hardware, and we need to effectively manage all these things. And so now what we are trying to do is we are trying to start building materials that behave in a quantum mechanical way. So then it rises to the second quantum revolution, where quantum computing has become very prominent. So this is the definition of quantum computing. This is one of the definitions, where it's a process of manipulating quantum mechanical systems, so which are also called as qubits. So right now, people are manufacturing multiple types of qubits, like for using photons, using superconducting qubits, and all. So still it is a debate which one works for which purpose. Almost there are 7 to 8 different kinds of qubits, like ion trapped qubits and NV centered atoms in the diamond and all such things. So what are these used for? These are used to process the information using the quantum mechanical principles, because as we are using quantum mechanical systems like qubits, so they use quantum mechanical properties of superposition, entanglement, and interference. Right? So how are they different from classical computers? So if you see, there will be only on and off for a classical bit, whereas quantum bit consists of superposition of both 0 and 1 at the same time. So this is the hardware property of a quantum bit. This has nothing to do with the logical ability. So as a quantum bit is designed such a way that it can hold the multiple states at the same time. So it is the ability of the quantum computer to deal some special problems. It cannot deal all the problems. So it is a misnomer that people think that quantum computing can solve any complex problem. No, quantum computing can solve only some problems that are suitable to be posed on a quantum computer. So coming to the basics, so these works on qubits are also called as quantum bits, which are represented using two basis states, which are in Dirac notation. So ket0 and ket1. So this symbol is considered as ket. So ket0 and ket1. So if a quantum bit lies in a superposition of ket0 and ket1 at the same time. So there is all this is all linear algebra, and a lot of math is involved in that. So I'm not covering all those things due to the interest of time. So it can be a linear combination of basis states. So 0 and 1 are the basis states. And now you can keep your quantum bit in a superposition, which is a quantum mechanical property, which can be a linear combination of both the basis states. So mathematically, it is represented as ket psi, where alpha ket0 plus beta ket1 is the state. So alpha and beta are considered as amplitudes of the quantum states, and it is according to Bond's rule, it should always be one. And these things are basics of quantum computing, the mathematical basics and all. So you can, if you're really wondering how this happens and all, you can refer to the Mike and Ike textbook. This is considered as almost a very famous textbook, considered Mike and Ike. So quantum information and computing. So you can have all those basics in that. And the state of qubit is indeterminate, as we consider that it will be in a superposition of both 0 and 1 at the same time. It will be in indeterminate state. Only when we measure this quantum bit, you will get some information out of it. So it is not like a classical bit. So whenever we start processing, the quantum bit will be in a superposition of different states at the same time. And then in order to get some information out of it, we need to measure that. So only measurement will allow us to take one of the two definite states. Whereas classical computers work only on classical bits. It will be just on and off. Okay. So yeah, coming to this, there is no intermediate state in classical computation, whereas quantum computation can take multiple intermediate states in between 0 and 1. Yeah, so these are some of the differences between quantum computers and classical computers. So quantum computation power increases exponentially as it is in a superposition of both 0 and 1 at the same time. I can represent the states in multiple forms. Say, for example, you have one qubit, I can represent it using ket 0 and ket 1. If I have two qubits,
इसमें
so
हाँ
each state can be each qubit can be represented using ket 0 and ket 1. That way, I'll be able to have multiple states at the same time, like 1 0 1 1. So sorry, 1 1. So there are four possible states with two qubits. That way, if I have one qubit, it can be represented in two states. If I have two qubits, it can be represented in four states. Sorry. And if I have three qubits, it can be represented in 2 power 3, 8 states. So that way your computational power is increasing exponentially, not linearly, like in a classical computer. Next, coming to the qubits, these are manufactured using subatomic particles. I'll tell you what are the different websites you can refer to so that to keep updated on what's happening in quantum field. And quantum particles can exist in two discrete states, as we discussed. And classical computers are made of CMOS circuits. Sorry. And so, as we use quantum processing units, so quantum computers consist of quantum processing units, QPUs. Your classical computers use CPUs, central processing units. And QPUs are can only solve specific problems. As I mentioned before, it can solve only specific problems. Not all problems can be solved. So like you cannot just design a game kind of thing on a quantum computer, something like that. It's too costly to do that. And it's also not suitable also. So it can solve only specific problems. And other important thing is quantum bits exhibit entanglement. That means you might have heard about Einstein's Podolsky-Rosen EPR paradox. So entanglement states that if two qubits, say qubit 1 and qubit 2 are entangled, there is a process of entanglement. We can entangle two qubits. And now whatever, even if I take these two qubits to some other distance, Q1 and Q2, whenever I modify Q1, there will be some effect of that on Q2. So this is considered to be a kind of, some paradox kind of thing, where Q1 and Q2 can be. This is not just a kind of coincidence. It's a kind of coordination. So again, this is completely different science in quantum mechanics. So you can always refer to that if you are interested in that. So quantum computers are not a replacement for classical computers, and they are not universally faster. This is the truth that we need to consider. So coming to different mathematical basics of quantum computing. So the information processing in quantum computers are qubits, and qubits operates in Hilbert space. And now people are trying to develop qubits where we have three states, not just 0 and 1. We'll also be having 2 as a basis state. So till now, qubit consists of 2 basis states, whereas qubits consists of 3 basis states. And this is the vector representation for the computational basis state of ket 0 and ket 1. So these are all used to perform linear algebra and mathematics for that. So now, whenever you consider a qubit, we observe that it will be in multiple states at the same time. So now to push this from one state to another state, what can we do that? How can we do that? So in order to do that, we need to use quantum gates, which are unitary operators in matrix form. So this is a matrix form where if ket 0 is the initial state and you use this unitary to modify this state to some other state. So u ket 0 refers to a mathematical state where ket 0 will be modified using this unitary and will be converted to ket psi. So this is the operation. This operation is considered as a quantum gate operation, where your basis state or the initial state will be modified using a unitary. And then it will be converted to some other state, which is superposition of 0 and 1 at the same time. So all these things are mathematically done. We'll see in a couple of minutes how it is done. So according to, as I told, according to Bond's rule, so you should be always considering mod alpha square plus mod beta square will always be 1. Okay. Right. So now there are different kinds of qubits. So there are single qubit gates and there are 2 qubit gates and all. So single qubit gates, this is one of the example gates, Hadamard gate operation. As we are discussing superposition, how to create a superposition, take a qubit in initial state, pass it through Hadamard gate, then you will get an equal superposition of both 0 and 1 at the same time. So this is done this way. So this is your initial state and this is your unitary, and you will get a ket psi, which is equal superposition of both 0 and 1 at the same time. So this unitary belongs to the Hadamard gate, and this is our initial state of the qubit, and mathematically it is represented this way. Then it pushes into superposition of both 0 and 1 at the same time. Because if you observe, you will get 1 by root 2 ket 0 plus 1 by root 2 ket 1. So now if there is to calculate the probability, I'll square this. So there is a 50% probability that after measurement, my qubit appears in state 0 and 50% probability that it appears in state 1. So that is the advantage of Hadamard gate. If you want to strictly push your qubit into superposition, you can use a Hadamard gate. Okay. Then there are also rotational gates. So rotational gates are also very important in order to create quantum circuits and algorithms. So single qubit rotational gates are Rx, Ry, and Rz. As I told, there are multiple quantum gate operations. So quantum gate operations, you have S gate, you have T gate, there are multiple gates. So, but mostly for information processing related to computer science, we use Hadamard gate, we use rotational gates, and we use CNOT gates. So these are the most prominently used gates in computer science for solving computer science problems. And this is the again the math behind the rotational gate. So if your initial state is get zero, after passing through RY gate, it will be pushed into this particular state. Okay, so where theta is the angle that it makes with that particular axis. So uh, with uh, with respect to y-axis, this is the angle. The similar way you will have all for x-axis and also z-axis. Now another important gate is C0 gate. So in order to study C0 gate, we need to understand what 2-qubit gates are and what are the basis states of 2 qubits. So as I told, if you have 2 qubits, you can have multiple states, can 0, 0, 0, 1, 1, 0, and 1, 1. So how are these formed? As we see 2 qubits, this is the tensor product, and you get this particular state. So mathematically, this is the operation. And now, in order to use or in order to entangle 2 qubits, you should perform again some unitary operation on those 2 qubits. So as we discussed, entanglement refers to if you have qubits Q1 and Q2, you do some operation on these 2 qubits, and then it will be these 2 qubits will be entangled. So that operation is a C0 operation. So if you see, there are binary operators are also in order to modify our state. So now C0 gate, how it works is that the first qubit acts as a control qubit and second qubit acts as a target qubit. So initial state of a qubit is 1 and in another initial state of another qubit is 1. So consider this Q1 and Q2. Now Q1 and Q2 are passed through this C0 gate. Then what happens is that this is mathematics behind that. So what happens is that whenever the initial state of the control qubit is 1, then the target qubit will be flipped. So as the state of the qubit is 1 here, the target qubit is flipped. So target qubit is 1, so it is flipped to 0. So the final state becomes 1, 0. So an initial state is 1, 1, and it is passed through C0 gate, and the final state becomes 1, 0. So that is how we can perform entanglement on these 2 qubits. So the fully entangled circuit, I'll explain later. So now, so you might be wondering how can we use these operations in order to create or solve some computational problems and all. So in order to solve any computational problem, you need to first prepare the state. So say, for example, you have some data, you use this data to prepare the initial state of the quantum system. So what do I mean by quantum system? If you have 1 qubit, this is a 1 qubit system. If you have 2 qubits, 2 qubit system, 3 qubits, 3 qubit system, n qubits, n qubit quantum system. So now in this circuit, you can see 4 wires. So each line in a by the way, this is considered as a quantum circuit where each line is represented as a wire and each wire corresponds to a qubit. Now you have some data and you convert this data to initial state. So there are operations to do that. I'll come to that. So you have some operation, say you have some unitary operation you use this data in order to prepare this unitary so that you can have this initial state. Now you have multiple other unitaries like UA, UB, UC, UD, so on, in order to convert this particular initial state to some other state at the end. So all these unitary operations result in some computation, and the final state is the state of the computation system you want. So how can we attribute this to solving a problem? Say you have some data and you use this data in order to prepare some unitary. So now if you want to classify this data or if you want to get some information out of this data, you need to prepare these unitaries in such a way that it gives you the result you want. So that is the idea of a computational algorithm. So you have an algorithm, you design it as a quantum circuit to solve a problem. Okay. So each line is considered as a wire and entire unitary operations are considered as a quantum circuit. So this is an illustration of a complete quantum circuit. But anyway, so we'll be looking at multiple quantum circuits in that. So finally, as we see that here we actually need to measure in order to get the result. So in order to get something out of it, you need to measure that. So that is why result is obtained only after measurement, right? So now how to measure? So again, there are mathematical operations to do that in linear algebra. By the way, linear algebra is mandatory thing you need to know, before you start doing any quantum thing. So same thing for machine learning also. So yes. So this is how you usually measure a quantum state. So this is the initial, this is the quantum state. Now you add this part mathematically so that you get some result out of it. So these are the mathematical operations. So polyz is a very famous measurement operator where it is used to measure the qubits in order to get some information out of it. Why polyz? Because if you observe, if the initial state of the uh, qubit is 0, you will get 1 as output. See, as the initial state is 0, which is represented by 1, 0. So the output is 1. If it is 1, which is represented by 0, 1, 0, 1, you will get -1 as output. So this is a simple thing that can be used for binary classification, where you take some data, prepare some unitary in such a way that that unitary gives 1 for this particular data or minus for some -1 for some other data point. So that way this can be used for binary classification altogether. So quantum measurements can result in a classical value, and these classical values can be post-processed based on application. I can directly use this 1 and -1 if I can make the unitary that way. If not, the advantage of polyz measurement is if it is not in one of the strict basis states like ket 0 or ket 1, what we can do is you will get some value between 1 and -1. So even that value can be used and we can post process that particular value. Right? So this is a strict entanglement circuit where we use both Hadamard as well as CNOT gate in order to push two qubits in a fully entangled state. So CNOT won't push the two qubits in a fully entangled state, only this particular operation, Hadamard operation followed by entanglement can push it to a fully entangled state. So this is the mathematics behind that. I don't want to well deep into it. It'll yeah. Anyway, this is I'll share this slide so that you can look at these things, matrix operations and all. So yeah, as I told, it will push it into a equal superposition of both 0, 0, 0, 0, 1, so that if Q naught is state in 0, it is obvious that Q1 will also be in 0. And if it Q naught is in state 1, it is obvious that Q1 is also in state 1. So sorry, Q naught and Q1. So the advantage here is if you know that one particular state only by measuring one particular qubit and by deciding the state of one particular qubit, you will be automatically able to find the state of other qubit. That is why this is considered as a fully entangled quantum circuit. So now What are all these? So why are these important for machine learning? Why are these important for computer science and all? So now, if you see, the machine learning algorithms are efficient for big data analytics. However, the size and the scale of the data will always test the ability of the machine learning algorithms. So now what we are trying to find is we require some computationally efficient hardware in order to handle this size or dimensionality. And we need such algorithms so that I can handle this size and I can get good insights out of it. So then machine learning algorithms, machine learning researchers started looking into quantum computation to find what quantum computation can offer machine learning so that they can train the algorithms or train the models or something similar to training or processing using machine learning. So that is why quantum machine learning gained prominence in order to find some techniques where the quantum computing techniques can enhance machine learning algorithms so that we can handle this huge amounts of data because qubits are different. So they can handle superposition and entanglement, which are quantum mechanical properties. And also there are powerful tools in linear algebra related to quantum computing that can offer great speeds. So that is why quantum machine learning recently gained prominence. And of course, right now when we are in the era of NISQ, this is considered as NISQ era, where the qubits are very noisy. I'll show why they are noisy and how to measure that noise and all. So I'll walk you through this IBM Quantum Experience website so that you can see the error that each qubit is producing due to this noise. So what we can do is, as machine learning can adapt the noise. So in some machine learning algorithms, we even introduce noise in order to make the algorithm learn better. So as it is adapting, the machine learning process is robust to noise. So people started looking at quantum machine learning, where they can also help quantum computers to mitigate this noise using the strategies in machine learning. So it is like coordination is vice versa. Quantum can help machine learning and machine learning can also help quantum. So quantum computing techniques can be used to enhance this classical machine learning algorithms. So people started looking into finding quantum machine learning algorithms that can be solved on present day quantum processing units, which are NISQ, which are designed in NISQ era. So how to process the data using a quantum computer? You can either select both classical data and classical processing, or you can select classical data and you can use quantum processing. This is what our talk is focused on. So classical data and quantum processing. And you can also see in the future, there will be some quantum data and quantum processing. Like say, people are manufacturing many quantum hardware devices like quantum sensors, which are more accurate than the classical sensors. There they generate some quantum data and that can also be processed using classical processing. And the quantum data can also be processed using quantum processing. So right now, people are more focusing on classical data and quantum processing, and very less people are working on this. And the last one, quantum data and quantum processing, mostly physicists do this. And I think slowly the developments get into the computational field also. Right. So in order to solve complex machine learning problems, we need to find some good quantum computational techniques for that particular purpose. Right. So this is the approach people are using in order to solve any complex problem using quantum machine learning specific to big data. So I'm specifically selecting big data because whatever the data that we are generating right now is considered to be big data. So you pre-process the data, and then, as I told, you need to first place it onto a quantum computer as a quantum state. For that, there are different data encoding techniques. So what data encoding is going to do? It encodes the classical data into qubits so that it can be processed using a quantum processing unit. So, by the way, this completely is not a quantum processor. The quantum processor sits only here. So it is very, hand-sized chip that sits here. All this is a dilation refrigerator, which tries to cool this particular thing. This setup is for superconducting qubits. Other quantum computers don't look like this. They sometimes they look small, big, or medium sized. So now, so you encode the data so that this encoded data into qubits can be processed using this quantum processor. Of course, the qubits reside on quantum processor. And this can be done using state preparation using quantum gates. As I told, everything should be performed using quantum gates. So even state preparation is done using quantum gates. So this is the initial state, and this can be considered as your quantum gate, which consists of data. Say this unitary will have some information about data, and this together will modify a particular quantum state. So amplitude embedding is one of the basic encoding schemes which provides exponential scaling. So we'll see how it provides exponential scaling. I used that in one of my research articles. So next, quantum algorithm, what is this going to do? So it process and transform the state of the qubits, and mostly it will be, it looks like a parameterized layer which consists of quantum gates. So I'll show the example of a quantum machine learning algorithm. And then, so you should be able to measure that, and you can post process, and you can do analysis. So in order to do this particular thing, and in order to work on the IBM quantum computer and all, you need some tools. So PennyLane is such a framework, and TensorFlow Quantum by Google is such a framework. This is by Xanadu. And I personally like this. This is very easy to use, and also very like I use this from initial version. Now it is in 23 or 24th version. I started using it from version 1. So I personally like this. And TensorFlow Quantum by Google, it's very powerful. And the circ simulator used in this particular is almost powerful, and all the quantum simulators available. So TensorFlow Quantum is by Google. So which can also, you can also use the TensorFlow processing on manipulating qubits and processing quantum information. So these are two very famous tools, packages, which are in Python in order to do these kind of operations. Of course, there are many. I'll show them at the last. So this is an example of a quantum multi-class classifier. So this is simple. So you have some data, and you have some special purpose qubits, also called as ancilla qubits. These are you can consider them as a reserved, some reserved qubits. So use state preparation algorithm in order to prepare the data, and then you manipulate the qubits in such a way that they give you whatever the result that you want. Say, for example, you're doing multi-class classification, and imagine you have one hot encoded your data samples. So I'm considering all of you are aware of one hot encoding. So in order to give the results we want, so we should be able to do this supervised learning. So this is simply like an artificial neural network, okay, which is trying to classify multiple data points using a quantum computer. So if you observe the difference from the traditional things, so this is what that is differing. So entire processing is done on a quantum computer. So after the measurement, you will get some probabilistic values, and you can use them as a, 0, 1, 0 for one hot encoding and all. So this is an example circuit. So if you are interested in, you can go and look at this particular publication. So this is done back in 2021. And yeah, so as I told, it is very important for us to initially encode data into qubits. So what we are trying to do here is, so we are trying to encode or create a state preparation scheme where we can encode the data in form of unitaries. So that unitary is defined again as a mathematical operation. This is the unitary. And if you observe, this unitary is designed with data elements in this. So x1, x2, so on xn are the data points. So as I told, there will be data and you can prepare a unitary with respect to this data, and then you can modify the initial state to some other state get site. So this is the idea behind this. And this is the output from the original IBM quantum experience hardware that we tried and to test this particular encoding scheme. And this is working absolutely perfect on this particular computer. So this is the algorithm behind it. This looks simply like a machine learning algorithm. There will be k number of layers. So you can consider them as hidden layers. There will be theta or your parameters or the weights you can consider. And what we are trying to do is we are trying to modify these thetas in such a way that you get the desired result. So if you observe the class labels are being classified using, the data points are being classified using softmax function at the last. So yeah, so these are very prominent functions in machine learning and all. So I'm not dwelling deep into it. Hope all are aware of these machine learning things and all. Right. So these are the results on IRIS dataset. So we selected simple IRIS dataset, BNA, and wireless indoor localization dataset. And we used amplitude embedding, and also we used our own encoding scheme. And we observed that our encoding scheme is giving very good results. And as I told, you can look at these, how the strategy and implementation and all available in the research paper. And if you want the code, I can send it to you. Please uh, drop a mail so that I can send the code to you. As we are doing developments to this code, we are not keeping it open source on GitHub. So, but if you want specifically look at how it is working, you can always email me so that I can send it to you. Right? So what are the observations in this particular work? So what we are trying to do is we are using quantum machine learning in order to classify different data points, and we also did it on real hardware. But the important observations are we are using same type of quantum operation in each layer. Like the way we change the activation functions in hidden layers, we are not doing anything in such a way. Uh, so very deep quantum circuits are not feasible to implement, as I told. And noise is a concern right now. So if the circuit is very deep, you'll be adding noise at each stage so that the noise sums up at the last. So also, as we have only few qubits, it is very hard to handle very large data sets. Right now, the availability of qubits is very less. Uh, Still, it is on in research stage, and people are developing. So what we plan to do is, so we try to use some hybrid models in order to handle the huge amounts of data, and which are feasible to implement on at present quantum computers. So this is the idea. So what we did is you take some data, process it using quantum, again use that data and train a classical neural network. That's simple. So of course, the implementation and processing are a little complex thing. Uh, So level 1, we are resizing the images to nearest power of 2 as we used amplitude embedding. This is the basic step we need to do. And coming to the level 2, the quantum circuit for quantum representation of images. By the way, this is specifically done for satellite images. So as I did my PhD in ISRO, uh, I worked on satellite images. So each image is passed through a quantum circuit and we obtain some values out of those images. So those are considered as quantum representation of images. Then these values are stored and fed into a deep neural network so that we will be able to classify the scene. So, what we did is that as previously we observed that it is difficult to handle completely using quantum, we use this hybrid approach. So to simply explain how it is done. So if you have some image like 4x4 image, all the 4 pixels are considered, and these 4 pixels say those are A1, A2, A3, and A4. And we prepared an unitary in such a way that A1, A2, A3, A4 are represented as amplitudes of the quantum state in superposition. So again, you can go to the research paper and uh, take a look at it. So this is available in Springer Nature Quantum Information Processing Journal, right? Sorry. Yeah. So this is how using amplitude encoding we did this. And this is the sample circuit for say for example, if we want to encode 1, 2, 3, and 4 as A1, A2, A3, and A4. So this is the circuit for that. Okay. So and after quantum, as I told, once we perform encoding, you need to do some quantum operations so that you get some values out of it. So after many empirical results and after doing lots and lots of experimentation, we realized that this particular architecture is working well on the particular satellite image data sets. So this is CNOT operation followed by uh, rotational operations where you get some values out of it. And by the way, again, this is all matrix operations. I'm not going deep into that. So what we did is we took each image and each image is converted to some quantum representation. So every image, say for example, each image is 256 cross 256. So that way you will have 655 36 something similar to that. And using 8 qubits, we reduced that to 2048. It's a kind of dimensionality reduction kind of thing where we reduce the size of each image or we extracted by reducing the size in each image using quantum. And these 2048 features for an image are considered while training a deep neural network. So this is a circuit originally implemented on IBM Santiago quantum computer. And again, I'll show that in a couple of minutes. So, sorry. So this is what I told. So our features are stored in CSV files, and those features are used to train a classical deep neural network in order to get the output. Right. So these are the performance comparison graphs where we compared our hybrid quantum circuit approach with existing state-of-the-art CNN models specific to satellite image datasets. So these are the satellite image datasets that we used. UC Mercy's land usage dataset, 8 scene dataset, NWPU, RESAIC dataset and all. Right. So again, these are the performance comparisons. So we are also able to reduce the total number of trainable parameters as we use the representations of the images, not the images directly, in order to create a classification model. So again, there are pros and cons in this particular approach also. So the pros are it is extracting the quantum representations and it is feasible to implement on real hardware. And the training is also easy as we are not using very in-depth convolutional neural network kind of architecture. And observations are we did a lot of data augmentation in order to gain that particular or achieve that particular accuracy. So then what we thought is, okay, so why to use it in a separate way? Why don't we combine this hybrid approach into the convolution neural network itself? So then we designed a hybrid quantum convolutional neural network, which works for the satellite images along with the data augmentation scheme. So this is the data augmentation scheme we observed, we developed, where we took an image, passed it through a particular quantum circuit. Again, the quantum circuit that you are looking here is designed after a lot of empirical experimentation with multiple combinations of different gates here, different combinations of C0 gates and all these things. And if you observe, this particular approach is giving almost kind of edges are being detected because of that. So what we did is that we took an image, passed it through a quantum circuit uh, in a phase-wise manner. We took chunks of it because at present we have only few number of qubits to work. I'll show that too. And then you will be able to reconstruct this image this way. So coming to that, uh, this is the hybrid approach that we followed. By the way, 1 second. So what we did is specifically, we took an image, we passed it through a quantum circuit, and then we again added that image to the original image to the image that is obtained after quantum processing. So this is the image obtained after quantum processing, and this image is added to the original image. So in the next slide, you will see that particular image, which is a combination of both original image as well as the quantum processed image. So this is kind of noisy, but still the results are amazing. So we have the convolution layer, pooling layer, so on. We added a quantum layer in between. Again, penny lane allows you to do that. And so TensorFlow quantum package also allows you to do this particular or experiment this particular scenario. And so then it is finally passed through fully connected layer for the scene classification task. Right, so these are the experimental results. So as I told, the experimental results are very interesting. So we used one single data set and we synthesized it to multiple data sets. And if you observe, our approach is outperforming all the existing approaches. And you can again look at that particular paper in which is available in IEEE Sensors letters. So this is the paper that you can refer to in order to see the strategy and all. Then to further extend this, actually, this is suggested by one of my supervisors who is senior scientist at ISRO. He's working as a head of high performance computing systems, Dr. Raghavendra. I also did my research under Dr. B.S. Manoj from IIST. So this is their idea. So they asked me to implement the quantum processing techniques on SAR images where the SAR images are different from optical images. So we use the quantum processing in order to do that particular things. Okay. So now, so there, for example, you have a image and you have a quantum circuit, and you are able to process that, and you can get some SAR images out of it. So these SAR images are specifically a observation of the quantum circuit. So this is the original image and this is the SAR image obtained after quantum processing. So if you observe, this is the original SAR image and this is the SAR image obtained after quantum processing. So even though you observe this particular noise in the image, you can see that there will be definitely some information. See uh, I'll show you the results. You can observe that. So again, this is another. So this is another way of doing quantum processing. Again, these are some
Avinash,
of
sir,
the. Yes, ma'am.
please try to finish by 3:30 because
Sure,
next
sure.
lecture is that of Manoj, sir.
Yeah, yeah. Okay, sure. So what? How much time do I have? I cannot see the
You
clock
have
here.
around 20. You have around 20 minutes.
Oh, absolutely. And then I'm almost at the end of the
Fine,
presentation.
fine, fine. Because I do not want him to wait.
Yeah, yeah. Even I don't
Yes.
want him to it. He's my
Okay,
supervisor.
okay. Yes, okay.
Yeah. So these are the results, experimental results for that. So now coming to the previous workflow that I discussed. So if you see, these are the steps where we can introduce quantum into the machine learning lifecycle. Uh, so you can clean the data or you can pre-process the data the data augmentation thing we did as a part of data pre-processing. So you can use some quantum processing in order to do something to your data. And then instead of just using classical models, you can always introduce quantum here and try multiple models. See, one thing is pretty sure you cannot guarantee that the quantum model is going to give very good accuracy, but as it is a very interesting research area, you can try them and you can come up with good architectures or methodologies that we can improve the machine learning process. Even slight improvement is also very crucial in some applications. For some applications, the slight improvement is not sufficient. So then you can also improve your models and you can use optimization. There is another research area called quantum annealing, where quantum annealers are used in order to optimize many mathematical problems. So you can also look at this particular area also. So that is what the point I want to drive. Uh, you can introduce quantum in these stages, not the other stages, because not other stages are very well established, and you cannot waste time on trying to identify how to use quantum in those areas. So these are the areas you can always try and publish. And coming to the future research directions, specifically to the work I have done. So you can also come up with qubit encoding schemes, which are data specific. You cannot do same thing for text. You cannot use same circuit for image. You cannot use same circuit for some voice data or something like that. So you should develop data specific qubit encoding schemes. And there are no hybrid models existing for numerical data. You can also do a study and observe the impact of the deep quantum circuits on that. And nonlinear hybrid models and nonlinear complete quantum models are also a good research topics. Nonlinear complete quantum models, I mean, instead of using convolution layer, pooling layer, quantum layer, you use all quantum layers, but specific to some solving a particular problem. So yeah, these are some of the future research directions that I have proposed in my thesis. But always there is a scope that the research grows and it is being extended. And even now we can see quantum vision transformers. So people are working on the area of transformers also. And yeah. So how to contribute to quantum community, or how to get something out of quantum community? You try to be a research volunteer, get into some research group, somebody where somebody is working in quantum, and then you can build your own quantum workforce in your university, and you can publish research articles. You learn some topics and go as resource person or delegate to some workshops, tutorials, or seminars or conferences. Then you can develop the network in that particular area. Uh, so that's all. So finally, I want to end on a philosophical note. After this, I'll be showing some resources to learn quantum. So this is one of my favorite quotes by Richard Feynman. He's considered to be the father of quantum. I mean, like he's not exactly father. There are many people who developed quantum computing and all, but he's the man who initialized all these things. So fall in love with some activity and try everything and keep minimum with all other things, specifically other computer science things. If you want to try quantum, we should be looking at both classical and quantum together. So thank you.